Are you ready? Okay, so I introduced a nice function last time, which is called an exponential function, and actually I should have emphasized it's called a natural exponential function. Okay, so I'll write that. Okay, because I almost always use this function, and we do not say it's natural exponential function, we just say exponential function. So, 2 to the x, 2 raised to the power x, that's an exponential function. 3 raised to power x, 1.7 raised to the power x, these are all exponential functions. Okay, and this exponential function is to the base 2. Base is 2. For this exponential function, the base is 3. And for the exponential function that we have seen, the base is e. And e is around 2.7 something. Okay. Okay, so let us recall what natural exponential function is. So I defined it as limit of this form you should remember, okay? I emphasize this form you should remember. I'm putting limit, okay, because this is what you are going to encounter when you are doing certain things. So it will naturally come out, and then you will be able to identify it as a natural exponential function. Okay, I will not always say natural exponential functions. Sometimes I'll just say exponential function, and it will be understood. Is that okay? And that is what was defined to be. Okay, this means this. Okay, that is what these 3 horizontal lines mean. And then we found that exponential of x, or exponential, natural exponential, or exponential to the base e is, it has a series representation. So it's a series, right? When you have this infinite terms added together like this, it's a series representation, and the series representation is (1 plus x plus 1 over 2 factorial x square okay, so they are infinite terms, and as you can see, okay, one has to argue, but you can see that this coefficient becomes smaller and smaller as you go further in the series, right? So actually it will go to 0. The coefficient goes to 0. It's 1 over infinity basically. Most importantly, we saw that exponential of x can be written as e to the x, right? This we proved that we can write it this way. Now I just like you want to know how a sine function looks like, how a cosine function looks like, how x square looks like. I want to show how e to the x looks like. Okay, we want to see this. So what I will do is I will plot this exponential function 2 to the x. So this exponential function is to the base 2. Then I will plot this exponential function, and because e comes between 2 and 3, so I will also plot e to the x, and then we will compare all these 3. Is that okay? Good. So let's or graphical, G-R-A-P-H-I or G-R-A-F-I?
PH.
Graphical representation. What happened? Careful, this will fall down. So, let us look at this table. Okay, so here I'll put values of x, here I will put values of 2 to the x, and here let's put this. So it's coming in the camera, right?
Yes.
So when x is equal to 0, when x is equal to 0, what is 2 to the x? 1. Very good. When x is equal to 1, 2 raised to the power x is 2. When x is 2, that's 4. When x is 3, that is 8. Okay? When x is minus 1, then it is 1 over 2, which is 0.5. When it is minus 2, it is 1 over 4. When it is minus 3, it is 1 over 8. Okay? Now let's plot. Write down the values of three to the x. So let's start with 0. 3 to the 0 is 1. 3 raised to the power 1 is 3. 3 square is 9. 3 cube is why? What happened? I'm having a lot of trouble today. Anyway, is 27, and here 1 over 3. So 3 power minus 1 is 1 over 3, that is 1/3. Okay, this got disturbed actually. Anyway, and this is 1 over 9. This is 1 over 27. Okay, so one thing you see that these exponential functions never become negative, right? For both negative and positive values, they are always positive. So let's plot this. You stop doing that thing. So let's plot okay. Not good. Okay, this is fine. So I have here one, 2, 3, 4, minus 1, minus 2, minus 3, minus 4, okay? And this is 0. So 0, 1, 2, 3, 4. And minus 1, minus 1, minus 2, minus 3, minus 4. Okay? So let's look at 2 to the x, 2 raised to the power x. So first I should mark here also 1, 2, 3, 4, 5. Okay, and it goes up. So at x equal to 0, 2 to the power x is 1. So I have a point here. Then at x equal to 1, you have 2. X is equal to 1, you have 2. X is equal to 3, you have, x is equal to 2, you have 4. So at 2, you are here. Okay? You see, it's increasing fast. At x is equal to 3, you are at 8. It comes here. At x equal to minus 1, you are at half. So this much is 1, so half is somewhere here. So I'll be here. At x equal to minus 2, you are 1/4 of it. So this is half. Half of that is 1/4. So it's somewhere here. Oh my goodness. Somewhere here. Okay, and this is 1/8. So somewhere here. Now let's draw a curve. So this is for what? This is for this. And this is still white, and this one I'll make pink. So 2 to the x is something like this. Looks ugly. It's fine? Okay. That's 2 to the x. So let me write down 2 power x. Let's look at 3 power x. So as you can see, for negative values and positive values, for both of them, this is positive. So it never becomes negative. 3 power x. So this is for x equal to 0, it is 1. So you are here. At x equal to 1, you are at 3. At x equal to 2, you are at 9. So you see, this one is increasing much faster. You are already here. And x equal to minus 1, you are at 1/3. So minus 1 is 1/3, so roughly here. And x equal to minus 2, you are 1/9. So it should be below this value, so it's already here. So if I plot this, let's choose red. So it should be something like this. What happened? I chose red. So is that okay? So this is 3 power x. So if I have 4 power x, it will rise much more steeply, right? Because you see 4 power x, the values will be increasing much faster. And if you have lower values, it will be here. And you see at x equal to 1, they cross. So at below x equal to 1, 3 power x is falling faster than 2 power x. So where will e to the x lie? E power x will lie somewhere in between. So it will be like this, coming somewhere in between, it will come, and then it will go between these two. So that's how e power x will look like. So I will not make the table of it. Good. So I'll just make a rough sketch for that. So e power x will be like this. So at x equal to 0, of course, they all will meet. Something of this sort. Very ugly. But you understand. Okay? So that is e to the x. So that's how this graph looks like. And I emphasize, e power x is always positive. never takes a value 0 for any finite value of x. Only when x goes to infinity, when x tends to infinity, this function tends to 0. Okay?
Tends to minus infinity.
X tends to minus infinity. Did I say infinity? Okay, x tends to minus infinity. Now we can answer this question. You remember here? Plus minus. We had two options. See, from here, this exponential of x over 2 square, that thing is exponential of x. Then I take a square root, then the solution is exponential of x over root x over 2 is plus minus exponential of x. And I didn't take exponential of the negative solution, because at this stage I had not shown you that it is e to the x, which is always positive, right? But now you understand why I had dropped that one. Okay, so we have a bit ugly looking plots. Exercise, and make sure you do it. Plot 1 over 2 to the x on the same graph and 1 over 3 to the x. Plot, what happens suddenly? 1 over okay, you should be already able to guess what it will look like. You should do this and compare. See, these values are just interchanged, right? Anyway, so do it. No, it can never become negative. No, do it carefully and then you will know. Yes, correct. That is how it will be. Very good. So, good, in the third attempt you got it. So, yeah, correct. See, after all, when you write, this is 2 power minus x, right? 1 over 2 to the x is 2 power minus x. Okay, good. Now, we are studying all this under differential calculus. And I have told you a function. What's the first thing you want to do? You want to differentiate it. So let's differentiate. Okay, and I like differentiating. So derivative of e to the x, okay, or exponential of x. So what is d over dx of e to the x? This is d over dx of 1 plus x square over 2 factorial. Okay, fine. So I'll differentiate term by term. Okay, so I will the derivative of sum I will use as write down as sum of derivatives. So what's the derivative of 1? What's the derivative of x?
1.
What's the derivative of x square?
2x.
So you have 1 over 2 factorial times 2x. What's the derivative of x cube? 3x square. What's the derivative of x to the 4? 4x cube. Agreed? Now this is 1 plus 1 over 2 factorial is 2 into 1 factorial, so 2 cancels. Is this fine? So I am using any number r factorial is equal to 1 into 2 into 3 into so and so forth up to r, right? So this I can write as 1, this I can write as up to r minus 1 is r minus 1 factorial times r. Okay, so what I am doing is I am writing always the denominator as, for example, here 3 times 2 factorial, so that 3 I will cancel. 4 times 3 factorial, so 4 I will cancel. So this is 1 over 1 factorial x plus 1 over 2 factorial x square plus 1 over 3 factorial x cube. Do you know this thing, what you have got? What is that?
e to the power x.
That is e to the x again, right? So the nice result is, if you differentiate e to the x, then you get e to the x again. Box is not nice. Fine? Okay, very good. So let's proceed with this result. This is fine, right? Let's start with this. So, how about the second derivative? d2 how about d2 over dx square of e to the x? Well, that's d over dx of d over dx of e to the x, right? That's the first derivative. This is the second derivative. But first derivative gives you again e to the x. But differentiating this gives you again e to the x. Right? So differentiating twice again gives you the same thing. And you can, as probably you can see, if you differentiate it, just differentiate it again. So that will be third derivative. That will be differentiating this. That again gives you e to the x. So you have d, when you put n like this, it means nth derivative. Oh, sorry, no. So no matter how many times you differentiate this guy, you get the same guy back. Okay, so that's a very special property of exponential function. So, good, that is good, that's nice. Now I'll give you derivative of another exponential of, let's say, 2x or exponential of 3x. I'll get a result, but then I will tell you a general theorem of which that will be a special case. Is that okay? So let's try to evaluate. Okay, where k is some constant. It could be 2, it could be 7, it could be whatever. It could be e also. It could be a negative number also. So, to do this, first I need the expression of e to the kx. So, what is e to the kx? Is 1 plus, tell me, kx plus 1 over 2 factorial kx whole squared plus 1 over 3 factorial kx whole cube and so forth. Okay. So let's differentiate this. I'll differentiate term by term. So first term gives you 0, second term gives you k. This one gives you, what does it give? So 1 over 2 factorial times k square, that's a constant. That is there. Then you have x square. When you differentiate, you get 2x. That 2 kills that 2. So you get k square times x 1 over 1 factorial. Okay, just like before. Here you have k cube 1 over 3 factorial but differentiating x cube will give you 3x square. So that 3 will kill the 3 in the denominator and leave behind a 2 factorial. So you get 1 over 2 factorial k cube x square. Good. Pull out a k from every term. Overall k, it is 1 plus x plus, because 1 factorial is 1, plus 1 over 2 factorial x square. No, sorry. Here kx, and here it will be k square x square. So I pulled out a factor of k from here, so it leaves behind a k square x square 1 over 2 factorial plus the next term will give you k cube x cube and so forth, right? So this is k times e to the kx. So if you had just e to the x, differentiating gives you e to the x. But if you have e to the kx, differentiating it still gives you e to the kx. But that k also comes out. Okay? That's what we have seen. So this is a special case of a more general rule or a theorem, which maybe I'll prove next time or leave as homework. We'll see. It's simple one-line thing. So, but what I'll do is I will tell you the theorem, and we will do some examples to get some practice. Okay? I think we have almost done all the functions that are studied at this age. So we have done polynomials, we have understood square roots, cube roots, hopefully, sines, cosines, trigonometric functions. Inverse functions we have not done, inverse trigonometric functions. Okay, that probably you can do on your own, or maybe I'll do, I don't know. But we have done also exponential function. One function that I want to introduce is logarithm. Okay, log function. That I will do later. A more natural thing will be to do it now. But I want this thing to settle down. Okay. So once this is part of your understanding, we can go to log. But before that, let's introduce what is called chain rule. Okay, it's not a rule that I have made or someone has made. It's a theorem actually, you can prove it. So theorem is this. Suppose you have, okay, let's look at this. Sine of x, that you want to know how to differentiate. What is that? Cos of x. How do you differentiate this? That you don't know. Okay, so I'm going to tell you the rule which you have to use to do this, and of course that rule can be proved. So this is sine function applied on another function of x, which is x square. Okay, so let's call that x square as a function u. Okay, so sine is acting on u, and u is the function of x, right? So in general you will have this. A function g of x, okay, and there's another function f which takes g as the argument, right? So in this case g is x square and f is sine. Okay, that's a composite function. It's a composition of f and g. Is this fine? You understand this? So the rule is equal to, so what we'll do is we will write u as g of x. Okay, so we'll denote g of x by u. So you see, when I took e to the 2x and differentiated, I still got e to the 2x. If I differentiate sine x square, I am still differentiating sine function, and derivative of sine is cos. So I expect cos to come. So that is what it comes. So when you differentiate f with respect to u. So if f is sine, derivative of that will be cos. So that is there, times what happened? Times du or dx. So df, the derivative, okay, I have changed the notation. That notation I have not never introduced. So I should not do that. So it is d over du of f of u times d over dx of u. Okay? So that's the rule. I'll give you some, this is called chain rule, and that's going to be extremely useful. So first let me give you some examples of these composite functions. So okay, so few examples here. You can have sine of x cube, right? So your g is a function of x. In this case, that function of x is x cube, and f is sine. So sine of x cube. You could have, let's say, e to the 5 square root of x. So in that case, what's g? G is 5 root x. And what is f? 5 is the exponential. Okay? It's not e. 5 is not e. It is taking g and putting in the exponent. Okay? Another example, it could be so what is g in this case? 1 over square root of x cube plus 1. And what is f? F is sine. Okay, one more. Sine of 2x. Gx is 2. So let's do some problems which will give us some experience with. So I'll start with algebraic functions and we'll move to trigonometric and then exponential. Is the rule okay? So let's take some examples.
Same.
Hmm?
We can find the derivative of these functions.
Sorry?
We need the derivative.
We can. But I want to go in an order. I don't want to take everything. I mean, we can, of course. So differentiate the following functions with respect to x. Okay? So I'll give you and you do it parallelly and let's see whether our results agree. So I've written down a few here. X square plus 1 square root. Problem number 2 is x cube minus 2 cube root. Problem number 3 is x square plus 1 square root of that in the denominator. Okay, let's do this. So x square plus 1. So I want to write this as f composition g of x. So the way to do is, so derivative of this is what? Is df over du or d over du of f of u times du over dx. Correct? So what do you want to take as u here?
X square plus 1.
Okay, good. So we'll take And what is f? F is the square root, right? So it's better to write this one first as x square plus 1 to the half, right? So this is so we are solving problem number 1 right now. So x square plus 1 square root is x square plus 1 raised to the power half, right? Now when I will write as u to the half. Is that okay? Now what's the chain rule? Chain rule says take this function and differentiate with respect to u. So it is d over du of u to the half. Then you take du over dx. Is that fine? This is what we are doing. So that's the derivative, okay? So this is d over dx of, okay, how much is that? How much is this?
Half u to the power minus.
Okay, very good. Half u to the minus half. U to the minus half is 1 over root u. Times du over dx. This is half. What is u? U is x square plus 1 times what is du over dx? So I have to differentiate u. Where is u? This is u. U is x square plus 1. Okay? So I differentiate x square plus 1, that gives you 2x. And I cancel the 2 in the numerator and the denominator, between the numerator and the denominator, and I get, do you also get the same result? Is that correct? Show it to me. Yeah, but you should replace as well. Very good, excellent. Okay, let's look at the second one. So I'll just write here. So second one is, what is that? X cube minus 2. Okay, that's cube root of it. Okay, do it. Then we'll compare. So u I define to be x cube minus 3. So my function is, or the derivative is,
X cube minus 2.
okay, so it is basically u power 1 over 3. That's the function. Correct? So when I differentiate this, this is cube root. So first I differentiate this with respect to u, and then I differentiate u with respect to x, right? So it is d over du of u to the power 1 over 3 times du over dx. What is the derivative of u to the 1/3? It is 1/3 times u to the power 1 over 3 minus 1, right? The power decreases by 1 times du over dx. How much is that? 1/3 times, did I make a mistake? No. So 1/3 minus 1 is minus 2/3. So minus 2/3 means 1 over u power 2/3. So 1 over Is that okay? 1 over 3 times u is x cube minus 2, so it's x cube minus 2 raised to the power 2 over 3 Now du over dx, the derivative of this is 3x square. So the 3's will cancel. Any problem? So the 3's will cancel and it leaves behind x square over. Did I make a mistake? Huh? Okay, so you know how to differentiate these kind of functions. Then I'll give you two more varieties of examples. One with trigonometric function. Okay. Find out d over dx of sine of x cube plus x square plus 1 square root. Can you do that? So you should do it this way. Okay, look at this. Don't write du over dx, no need. Okay, that was when I am going to do, I am not going to do it that way. I am going to do it this way. This is equal to sine. When I differentiate sine, I get cos. Cos of what? Cos of that entire argument, right? So you understand, right? This is df over du basically. So cos of x cube plus x square plus 1. I made a mistake. I want to go slow. In this one, I want to go slow. Let me just change the problem. First, let's do this one. Okay, that's better. We'll do that one next. Differentiate this. So when I want to differentiate this, I will do it this way. First, when I differentiate sine, it becomes cos. And it gives you, that's the first factor, df over du, times, just differentiate the argument. So that gives you 3x square plus 2x. Okay, so that's your result. Now let's take the example of this. I want to differentiate sine of x cube plus x square plus 1. Okay, that's what I want to calculate. So I'll do it slowly. First, I define this entire thing, square root of this, as u. So u is x cube plus x square plus 1 under the square root. Okay, so this, using the chain rule, becomes du over dx, d sine u over du, times du over dx. Correct? Okay, but what is u? U is this. So let's call x cube plus x square plus 1 as w. Okay, so define w is equal to x cube plus x square plus 1. So you have now derivative of u with respect to x. But what is u? U is square root of w. Pay attention here. Okay. So u is, using this definition of w, square root of w. Okay. So now again I have, for this thing I should use a chain rule. So what is du? So let's write one more step. So this part is derivative of u with respect to x is basically dx of square root of w, right, which is the derivative of this is 1 over 2 root w. Okay, the derivative of square root of w So I am using the chain rule again and I am directly doing it. 1 over 2 root w times dw over dx. Is that fine? So we are here now. dw over dx, that's simple. So where do I stand now? I am here. So this is cos of u, but what is u? U is this. So x cube plus x square plus 1, the square root. Okay. Then I have 1 over 2 root w. What is root w? That is u. Sorry, something. Yeah, that's u. Correct, no? What happened? Yeah, 1 over 2 square root of x cube plus x square plus 1 times derivative of w. W is this, times 3x square plus 2x. So that's your result. Do you agree? Agreed. So you see, you can just repeatedly do this. So if I differentiate this, okay, cos of the argument times the derivative of this argument, but the derivative of this is again take using chain rule 1 over 2 root this thing, then differentiate the argument. So you don't write u, w. For first few times you can, you should. Then it should be mentally, you should be directly doing it. Okay, so this is an example of a trigonometric function, differentiating that with chain rule. Now I'll give you one final example. Final example, and it's a useful one. Differentiate d over dt of e to the minus, let's say, yeah, let's first look at this one. What is that? Can you do that? So I'll use again chain rule. The derivative of exponential function is the exponential function, right? Then according to chain rule, I should multiply that with the derivative of the argument of the exponential function. So it is d over du, d over du of e to the u, where u now is e to the minus t. E to the, minus, where u is minus t. Okay? Times du over dx, du over dt. But what is the derivative of u? U is in this case minus t, right? So du over dt of minus t. So this is again the exponential function e to the u, which is e to the minus t. Derivative of this is minus 1. We have to remember this one because when we start talking about capacitors charging and discharging, this function will appear. So I'll put d over dt of e to the t is e to the t, d over dt of e to the minus t is e to the minus t times minus. Okay, and you can check. Okay, do it orally. D over dt of e to the minus alpha t, where alpha is some constant, will be
minus alpha e to the power minus alpha t.
very good. These two we should remember. What is that? Okay, okay, we'll stop here then. Fine, so let's stop here. Okay, good.